this video we're going to look at force. So a lot of this should hopefully be a recap from last year. I hope you've already seen a lot of this application, so I'll go through it relatively quickly, and if you're comfortable with a lot of the concepts here, feel free to sort of skip ahead. So the main learning intentions for today are to explain the concept of force making objects motion change, explain what is meant by a balanced and unbalanced and a net force, and calculate the net force on an object. So a force is an action which causes motion to change or causes an acceleration. So basically it's changing the motion of an object by either making it accelerate, change direction, etc. We'll talk about that in more detail. The unit of force is the Newton, denoted by capital N. So if we measure a force and it's 10 newtons, we would just write 10 capital N. Often when we draw force, we represent it by an arrow, where the arrow's length is representative of the size of the force. So a really long arrow indicates a lot more force than a shorter arrow, and the direction that the arrow is pointing is the direction that the force is being applied as well. So in our picture here we can see Baby Yoda would have a small 5 Newton force pushing to the right and a bigger 10 Newton force pushing to the right, and they should be proportional, so the 10 Newton arrow should be double the length of the 5. What I want you to do is try and list as many forces as you can think of. So pause the video quickly and list as many types of force as you can think of, and then we'll come back to it. Some of the ones that you may have had are things like gravity, magnetic force, contact force, tension force, the normal force, drag force, friction, applied, spring, electric, strong, and weak. There may be other ones you might have said like push, pull, things like that. Push and pull are linked to applied forces. So if you mention that, that's fine. They are sort of bannered under the applied force as well. But it'd be interesting to know how many other types of forces you came up with. Sometimes there are other forces that people state that are not truly an actual force, but more linked with something else. So a really common question is, how much force is something? Like if I said to you, how do you feel about me pushing you with 10 newtons of force? You would go, I don't really know. I don't know how much 10 newtons is. Is that a lot? Is it a small amount? And this table will give you some examples. So firstly, by definition, 1 Newton is the amount of force required if I had a 1 kilogram block on a table and I wanted it to accelerate away at 1 meter every second, so it's speeding up by a meter per second every second, I would need 1 Newton of force. That's not particularly helpful. That's a pretty garbage definition. Another way to think of it is 1 Newton of force is the average weight of an apple. And what I mean by that is if I had an apple on my hand, the amount of force that that apple is pushing down on my hand with is about 1 Newton. 9.8 newtons is the amount of force that a 1 kilo block would push on you. So if you held a kilo in your hand, it would have a force of 9.8 newtons. So if you can think of it in terms of how heavy something is, it's not a good analogy, but how much force, which we feel as how heavy something is related to the mass in that aspect. 1 kilo feels like 9.8 newtons. Another context is 4,000 newtons of force is how much it would take to break your femur. And the femur is the strongest bone in your body, which is kind of your thigh bone. That is the strongest bone. It takes 4,000 newtons to break it. The bite force of the average human is 720 newtons. So unfortunately, no matter how hard you try, you cannot snap someone's femur with your teeth by biting through it. I'm not really sure why you'd want to, but in case you were thinking about it, don't. It's not going to work. However, an alligator has a bite force of 9,000 newtons, or 9 kilonewtons to abbreviate it. So that definitely could. In fact, it could bite through both of your legs at the same time and snap the femurs. That's quite terrifying. But in Australia, we do everything bigger and better, right? So we step it up and we say an Australian crocodile has a 16.5 kilonewton bite force, or 16,500 newtons. So you could take you and 2 of your mates and lie down and it could still bite through and snap all of your legs at the same time, because Australia. An airbag. If you hit if you hit an object at 100 kilometers per hour and the airbag is deployed, it hits you in the face with a force of 100,000 newtons. Now at first you're probably thinking, that sounds terrifying. Why would I ever want my airbag to go off? It's supposed to save me. However, there's a lot more to this. This is just the sheer amount of force, whereas we factor in the time it takes, and there's a lot of other aspects in physics we have to consider. It's not nearly as devastating as hitting the steering wheel or the windshield at that speed. It is still better. But you're just going to have to trust me. Airbag is a lot of force, doesn't kill you. The others definitely will though. Alligator will kill you. Let's consider a rocket. So Saturn V was one of the biggest rockets ever made for its time. It produces 35 meganewtons, or 35 times 10 to the 7 newtons of force at liftoff. That is how much thrust its engines produce, which is monstrous. So this gives you some context to a variety of different forces. What is a lot of force? 4,000 newtons, it's a lot of force. It'll break your legs. 1 newton, not much. It's an apple. So what do you weigh? It's often a very personal question. However, if you consider it in terms of physics, your mass and your weight are not the same thing. Mass is really a measure of how much stuff something is made of, and the other, which is weight, is a measure of the force that it's experienced because of gravity. So weight is often known as the gravitational force. You weigh different things on different planets because of the gravity. Your mass, however, does not change. Mass is always the same. You have the same amount of stuff, the same amount of atoms, etc. in your body, no matter where you are in the universe. So mass is kilograms. When you weigh something, you are actually measuring its mass in kilograms. Weight is a force, and it's a force in newtons. So how do you convert the two? How do I know how much I weigh? Well, luckily on Earth, gravity is 9.8. It's roughly 10. So the easiest way to do it with some accuracy is multiply your mass times 10, and you have the force that your body exerts. So for example, I weigh 95 kilograms, therefore I multiply it by 10, I produce 950 newtons of force on the ground. If I was to stand on someone's leg, I would put 950 newtons of force into their leg, which is not enough to snap their femur, thankfully, just by standing on it, but it gives you some perspective. You can imagine me standing on you is probably not comfortable. That's just shy of 1,000 newtons of force. So I want you to do the same thing. Use this calculator. It's very simple. Take your mass, what you've weighed, I don't like the word weighed, but what you've measured on the scales, or what you think your mass is in kilograms, times it by 9.8 to get a very specific number, and that is your weight in newtons. So that is the force that you deliver every time you touch the ground. So as we said, the arrow, both in length and direction, represents the force. A big arrow, lots of force. In this case, the arrow is pointing to the right, which indicates that the force is being applied to the right. Hence, the box will move in the same direction. We see these kinds of force diagrams all the time. So in all of these examples, we can see the different amounts of force. Classic plane example. Have a think for a second. What is the name of this force? We've talked about it last lesson. It is the thrust. So the thrust of the engine is pushing forward. This is the drag slowing you down. The lift is pushing up. And the weight, which we've now seen what that actually means, is pulling you down. Same thing applies for everything. In our football case, in our soccer ball sitting on the ground, in this case they're equal, so the ball doesn't move. The bird flying, the fish, let's call it a tuna, swimming through the ocean, forces. Always there, always doing stuff. So now we'll look at this concept of balanced and unbalanced. Ultimately what it means is when forces act in opposite directions and they're the same size, then they're balanced. So as we saw in the soccer ball on the last slide here, or we look at the book in this slide, we can see that there is a downward force due to gravity pulling that book down, but it's sitting on a table. So therefore the table is pushing up against the book to balance out gravity. Book is not moving. Book is not levitating in the air, is not sinking through the table. It's stationary, so we would call that a balanced force. If, however, the forces were not balanced, the thing will move. That is the key piece. If forces are not balanced, the thing moves or its motion changes. So let's look at an example. As I said before, the thing might change, but it doesn't mean it's no longer moving. So a really common example of this is called terminal velocity. For skydivers, for things falling through air, you can reach a point where the gravity pulling you down is balanced by the drag of the air pushing up against you, and therefore we have a balanced force. The misconception here is a lot of people think it's a balanced force so you stop moving. But that doesn't make sense, otherwise you would just start levitating in midair if you jumped out of a plane. You would never reach the ground. So let's look at this quick little video talking about terminal velocity in skydiving.
The MIT Skydiving Club just jumped out of an airplane. It might seem like a wild adrenaline rush, but actually, there's a lot more to skydiving than just jumping out of a plane and pulling a ripcord. Skydivers can control their falls. They can sit, track, flip, fly head down, make crazy hybrids, and even fly over to each other to dock.
When you're just falling a few feet, there's not much you can do on the way down. So how is falling thousands of feet through the sky any different? You learn in school that things accelerate towards the ground because of gravity.
But when things like skydivers fall for thousands of feet, another force becomes important.
Drag! Gravity pulls skydivers toward the Earth. But as we fall, tiny air molecules bump into us. Each tiny bump causes a little bit of force against our bodies. The hit from one air molecule may not seem like a lot, but when you add all those tiny forces up, you get a big force called drag, which pushes up, opposite to gravity. You can feel drag when you stick your hand out of a moving car window.
When the jumpers first leave the plane, there's not much drag acting against gravity, so they accelerate towards the Earth. As skydivers fall and speed up, the drag force grows, and the skydivers feel the force of more and more air molecules. But with this comes control, and by positioning our bodies, we can stop flipping by pushing against the air.
So, what if Banks and I want to jump together? Can we fall at the same speed?
Swathi has a lot less surface area than me, so you'd think that she'd fall faster. But actually, she's so much lighter than me that she has a tendency to fall slower.
But by reducing how much surface area is exposed to the air molecules, I can reduce drag and keep up with Banks. Drag can be used for more than just speeding up or slowing down. Moving your arms to the side and legs out generates extra airflow at your feet, which pushes your body in the direction it's facing. This is called tracking. To really use drag, air needs to push you hard enough, which can only happen if you're going fast enough. And that's why you can't track when you jump off of the high dive at a swimming pool.
Skydivers can also do things like turn in place to create formations with each other. Other positions like sitting, standing, and head down change the surface areas that jumpers expose to the wind. Since fewer air molecules hit their bodies in these positions, skydivers can reach speeds up to 200 miles an hour. Skydivers would prefer, though, to not hit the ground at 200 miles an hour.
Because they can't change the pull of gravity, they need to have as much drag as possible, so they open a parachute.
The large surface area of the parachute helps us to slow down so we can land safely.
Skydiving may seem like it defies the laws of physics,
But in the end, it's just playing with the wind.
So when we have the forces on an object that are different sizes, this results in a change in motion, such as speeding up, slowing down, changing direction. These are called unbalanced forces. So some really common examples we see is when looking at a moving golf ball. The force from the club causes the ball to move to the left. However, the friction is much larger and acts in the opposite direction to slow it down. As friction is greater in size than the force that was on the ball in the first place, it'll eventually slow the ball down and cause it to stop. In these examples, I want you to have a quick think about, are these forces balanced or unbalanced? Hopefully you said from the left, our rocket is unbalanced. We can see that the arrow is greater, but also the rocket is moving and it's speeding up as it launches off the ground. So therefore, this gravity force here is not balancing with the thrust. With our lizard friend here, the forces are balanced. Lizard is not falling off the tree, stick, whatever that is, and the arrows are in the same direction, so force is balanced. In this example, we've got a horizontal and a vertical aspect. So vertically, we can see they are balanced. The gravity and the buoyancy force of the water on the boat or the sail are pushing it upwards, so they're equal. However, in this direction, we can see that the force of the wind is creating a thrust forward and the drag is pushing backwards. This is greater, so the object will move towards the right. Looking back at our skydiver, we're going to look at this concept of net force. Net force is the overall force that's acting on an object. Basically what we do is we take the force in both directions and we add them together. The only catch is if one is in the opposite direction to the other, then we take the negative of it. So in physics we say that up is positive, down is negative, something to the right is positive and something to the left is negative. Just like we would see on a Cartesian plane when we draw our axes. We go up is the positive y coordinate, down is the negative y coordinate. So the same thing applies. So in this example, if we have 800 newtons of air resistance up and gravity has 1500 newtons down, I want you to think about what would the net force on this skydiver be. So hopefully you said, well, it's 1500 down, we minus the 800 up. You could have gone the other way around. You could have said it's 800 up minus the 1500 down. That would actually be a better way to do it. But in this case, it doesn't really matter too much, except that our answer should be negative. But because negative is down, I've corrected that by saying that we have a 700 Newton net force, and I can tell from my picture that it's downwards. So that's fine as well. So either way, you're going to get 700, but you'll either have plus 700 or minus 700. And as long as you know that it is down from our diagram, then that's completely fine. But 700 newtons is the net force on the skydiver. What if we want to add two forces that are in the same direction? In this case, it's even easier. We just combine the two forces, and because they're in the same direction, we simply add them together. So with our two people pushing the couch, this guy on the right is pulling it to the right with 100 newtons, and this lady on the left is pushing it in the same direction with 150. We add the two together, we get 250 newtons of force to the right. That is our net force on the couch. Now I want you to consider a slightly different example. We've got 4 children fighting over the same toy. Maya is pulling up with a force of 50 newtons. Jack is pulling to the right with a force of 70 newtons. Kato is pulling down with 50 newtons. And Rati is pulling left with 30 newtons of force. First, I want you to identify the forces acting on the teddy bear, and then answer the question. So figure out who is pulling which force, and then tell me what are the horizontal, the vertical, what is the net force on the object, and tell me which way the toy will move. Hopefully this is what you got. 40 newtons to the right is the horizontal, 0 newtons is the vertical because they cancelled out. Therefore the net force is 40 newtons right, and the toy will therefore move to the right. Using the same concept, applying it to a plane speeds up as it flies through the sky. What is the net force acting on this plane? We can see here, vertically they cancel out. Horizontally they're in opposite directions, so which option do you think will be the right answer? I've got another simulator for you. This PhET simulator is all about motion, and this is a great little program that lets you play around with net forces. You can increase the amount of force that these two people have in tug of war. There's other ones that involve friction forces, and it shows the arrows of friction. But I want you to have a quick little play moving around with some net forces. Time for a practice question. So in this example, we're going to use 9.8 as the acceleration due to gravity. So that is the gravity of Earth. And the gravity of the moon is 1.67. So remember we talk about weight and mass. We said you multiply it by gravity or acceleration. It's the same thing in this case. So for the first question, I want you to calculate the weight of a 60 kilogram student on Earth. Then tell me what the student's mass would be on the moon. Then determine the student's weight on the moon. And then if I had two 50-gram masses hanging from a spring, calculate the force that acts on them. The only thing that I would add to this question here is that your mass needs to be in kilograms. So we always use kilograms, and we'll see why in a video shortly. So pause the video here, have a go at these questions. Now we're going to look at some answers. So for the first one, we've got mass times gravity is weight. We just times the mass times the amount of force of gravity, 588 newtons of force for that student. On the moon, they are still 60 kilograms because remember it says the mass, and mass does not change no matter where we are. However, their weight on the moon will be their mass times the new gravity, which is the 1.67. So they'll only have 100 newtons of force against the ground. So basically 1/6 of the force they would have on Earth. If we had the two 50-gram masses hanging from a spring, we're going to have this mass times gravity. We've got 100 grams in total, so 0.1 kilograms. Times that by 9.8, we get 0.980 newtons of force from those two masses. So let's do a learning intention check. Can you explain the concept of force? Can you explain the terms balanced force, unbalanced force, and net force? And can you calculate the net force on objects given individual forces as we've seen in examples in this video? If the answer to any of those is no, you know what to do. Otherwise, I'll see you next lesson.